Next, we're going to study parameters of combinatorial classes of labeled objects. And again, we're going to extend the same basic methods that we used for counting in classes of labeled objects, but to study parameters. So we extend the basic definitions as we did before. We're talking about labeled classes that are sets of labeled objects that have a size function, but now they also may have an associated parameter. And we define the exponential bivariate generating function associated with a label class. And it's the same power series, sum over all objects in the class, z to the size of the object, u to the cost of the object, divided by the size of the object factorial. And we do that because the labeling introduces so many possibilities. We have the usual fundamental identity. If you're summing over all objects, you can group them according to the ones that are of size n and cost k and get a double sum with the familiar enumeration. And we use the same terminology. Z marks the size, U marks the parameter. We can extend it to multivariate generating functions because we could add an arbitrary number of markers. And if we want to know the number of objects of size n with value k, and we have the exponential bivariate generating function, then the number of objects of size n with value k is equal to n factorial times the coefficient of z to the n and u to the k in the bivariate generating function. And as usual, with the symbolic method, we specify the class and at the same time characterize the exponential bivariate generating function. So this is the transfer theorems, and I'll go through them very quickly because they're the same as before. Union is when we construct a class by taking disjoint copies of objects from two classes. The OGF that we get is the sum of the associated OGFs. Labeled product, when we take pairs of copies, one from A, one from B, and relabel them in all consistent ways as we have to for labeled classes, then we get the product. Sequence extends the product operation, and the generating function is 1 over 1 minus, always as before. And again, construction immediately gives the BGF equation as it did for enumeration. And again, this extends immediately to mark multiple parameters. So just a simple example, how many different letters are there in a three-word? In a three-word of length 1, they all have just one different letter. Of length 2, there's 3 of them that have one letter, and there's 6 of them that have 2 letters. Of length 3, there's 3 that have one letter, 1, 1, 1, 2, 2, 2, and 3, 3, 3. 6 of them that have 3 letters, all the permutations are 1, 2, 3, and the rest have 2 letters. And those are the cumulated and average costs computed as usual. So let's look at the use of exponential generating functions to solve this one. So we have our class of all m words. Our size is the number of letters in the word. Our parameter is the number of different letters in the word. So we have the exponential bivariate generating function defined in the natural way. So what does our construction look like? The construction for n words is sequence of set of letters, but what we want to do is mark the sets that are non-empty. The empty ones we won't mark, and that way we'll get the number of different letters. So it's a sequence of sets, but the non-empty ones are marked. So that immediately translates to this exponential bivariate generating function equation. Empty translates to 1, u to u, non-empty set, e to the z minus 1, and then sequence of length m is all of that to the mth power. So from that equation, we can evaluate that at u equals 1 and get e to the zm. And we can differentiate with respect to u and evaluate at 1, and we get this slightly more complicated expression, but when we divide the two, we get the familiar result. The average number of M words in a random, average number of different letters in a random M word of length n is M times 1 minus 1 minus 1 over M to the nth. So they're mostly going to be different as n gets large. All the letters are going to be there. So that's to be expected, and that checks with what we observed on the previous page. So here's another example. We could pick the frequency that we care about. So that's the number of different letters that appeared with any frequency. What about the number of letters that appear k times? So that's, we'll call that fk of w, the number of letters that appear k times. So so that's going to be, we're just going to mark the ones that are not equal to k, the ones that are equal to k, and the ones that aren't equal to k we won't mark. And so that gives us this simple EBGF equation. And again, evaluate at 1, we get back our number of M words. But if we differentiate with respect to u and evaluate at 1, essentially we show that the average number of letters that appear k times is M times n choose k, and this is a familiar occupancy distribution, which is what we'd expect. Again, just showing a simple probabilistic derivation using the symbolic method for M words. So what about this, which I used as a motivating example early on? How many permutations of n elements have k cycles? This is all the permutations of 1, 2, 3, and 4 elements written in cycle notation. And we can write out the distributions. So for example, the number of permutations of 3 elements with 1 cycle, there's 2 of them, the 2 at the bottom. The number with 3 cycles, there's just 1, that's the one at the top, and the other 3 have 2 cycles. Similarly, we get this distribution 6, 11, 6, 1 for permutations of 4 elements, and we can compute the cumulated costs and the average, 1.5, 1.8333, 2.0833. That's the average number of cycles in a permutation of 1, 2, 3, and 4 elements. And this is, again, easily analyzed with symbolic method on labeled objects using exponential bivariate generating functions. All we do is label the cycles. A permutation is a set of cycles, and we label the cycles, mark the cycles with u. So the generating function is e to the u log of 1 over 1 minus z. That's log of 1 over 1 minus z is for cycles, and u is the mark, and then set is e to that power. So it's 1 over 1 minus z to the minus u. So to enumerate, evaluate that at z equals 1. So the coefficient of z to the n and that is 1, multiplied by n factorial is n factorial permutations. To compute the cumulated cost, or the number of cycles, we differentiate that with respect to u, and then evaluate at 1. So differentiate this with respect to u, and then evaluate at 1. And you might need to practice your partial differentiation. If you want, write this as an x log, and you'll see that result, 1 over 1 minus z log of 1 over 1 minus z results. And then, therefore, the average number of cycles in a random permutation is the ratio of the coefficients of those two multiplied by n factorial, and that's exactly the harmonic numbers. So, and that checks with what we observed. The number of cycles of a random permutation 1, 2, 3, 4 is 1.5, 1.833, and 2.0333. So straightforward with the symbolic method, marking the parameter value with the second variable u. And again, we can go and compute the standard deviation. It's a square root of log n, so that one is even concentrated. In fact, this distribution is another well-known one. It's known as Stirling numbers of the first kind, the Stirling cycle numbers. So these are what we observe for 1, 2, 3, and 4. The horizontal exponential generating function for this is u times u plus 1 times u plus 2 and so forth. And then the vertical one is 1 over k factorial log of 1 over 1 minus z to the k. The one we derived, the exponential bivariate generating function, 1 over 1 minus zu. And there's arguments for getting both of these and extracting coefficients and so forth. Quite a bit is known about the Stirling numbers of the first kind as well. What about number of cycles of a given length? How many cycles of length r can we expect to find in a random permutation? It's just a matter of naming the parameter and then marking that parameter. With the cycles of length r, we'll mark with u. The ones that are not of length r, we won't mark. And so then we get an exponential generating function immediately from the symbolic method that is e to the log 1 over 1 minus z, but we subtract off the z to the r over r term and then add a marked one. So that works out to be e to the u minus 1 z to the r over 1 minus z. Of course, if you evaluate that at u equals 1, then we just get 1 over 1 minus z as before. If we differentiate with respect to u and evaluate at z minus 1, it pulls out z to the r over r. If we take the coefficient of z to the n and divide, and then evaluate at 1, and then divide, then we get 1 over r. The average number of r cycles in a random permutation is 1 over r. And that's an interesting result. There's one cycle, there's a half a 2 cycle, a third of a 3 cycle. So most of the cycles are going to be small in a random permutation. Okay, here's a different problem. How many ways are there to partition a set of size n? So we've got 2 elements. Either we could partition into 2 subsets or leave them in 1. There's 2 different ways. For 3, there's 5 different ways. 3 different subsets, all in the same subset, or 2 subsets. And for 4, there's 15 different ways. And actually, we'll prove the number, but we're also interested in knowing how many are there that are partitioned into k different subsets. For 3, as I just said, there's one that has just 1 subset. There's one that has 3 subsets, and the rest of them have 2. For 4, it's 1, 7, 6, 1, and we can compute the accumulated cost and the average. And maybe you recognize these numbers, but let's use the symbolic method to study it for now. We have the class of all set partitions. Our size is the size of the set, and our parameter is the number of subsets in the partition, and then there's our exponential bivariate generating function. The construction is a set of sets, except we're going to mark the subsets. Simple as that. So it's a set of non-empty subsets that are marked. So that's the set of non-empty subsets is e to the z minus 1. They're marked with the u. A set of those is e to that power. Evaluate that at u equals 1, and the exponential generating function to enumerate those is e to the z minus 1. And the accumulated cost is a derivative with respect to u of that, which it multiplies it by e to the z minus 1. And the average number of subsets in a random set partition is the ratio of that. Now these are getting to be complex calculations, and we'll need the complex asymptotics that we're going to study in the second half of this course to actually find out that number. But maybe you recognize the numbers. Actually, this is the Stirling numbers of the second kind, this exponential bivariate generating function. we had an ordinary bivariate generating function for the same numbers. The horizontal is the Bell polynomials, but now we divide by n factorial. And vertical is found by extracting coefficients of z to the n, and that's essentially the derivation that we gave. But again, there's another whole set of identities involved with understanding the Stirling numbers of the second kind. And here they are coming up in a completely different application with exponential generating functions. Finally, there's the combinatorial object, labeled combinatorial object called a mapping. We studied the derivation of generating a function equations for enumerations of mappings. It's a function from the integers 1 to n onto itself. We can write mappings as a digraph where every element has a link to whatever element it maps to. And we're interested in questions like how many connected components are there, how many nodes are on cycles, how many are on trees, and so forth. And again, if you want to see motivating applications of this, look in part 1 of the course. And this is a summary of what we did in the last lecture, starting with Cayley trees. A Cayley tree is a root connected to a set of trees, which gives the EGF equation C equals Z e to the C. Mapping components are cycles of trees, which is log of 1 over 1 minus C of Z. And the set of mappings is a set of components, so it's e to that power, which leaves the 1 over 1 minus C. So those are the EGFs, and in the context of this lecture, the point is we can use these same constructions to get generating functions for mapping parameters. So number of components, mapping is a set of cycles, so we're just going to mark the cycles of trees, and that gives us the number of components. So that's, it's e to the u log 1 over 1 minus c, which is 1 over 1 minus c to the u. So that's an EGF equation to describe the number of components in a mapping. Or if we want the number of trees, then we take a set of cycle and then we mark the trees. And that gives a completely different equation, although these symbolic manipulations are very simple. And that one's 1 over 1 minus u, C of z, for the number of nodes on cycles in a mapping, or the number of trees. So to find the moments and coefficients, then we're going to have to work with trying to find derivatives with respect to u, or extract coefficients. You remember, for enumeration, we needed advanced techniques, and we're certainly going to need advanced techniques from complex asymptotics, although actually these turn out to be handled with powerful general theorems that give the answers almost immediately. But that's a subject for second half of the course. I think at this point, I'll quote Philippe, that we can stop supplying examples now, because with the tools that we have, the combinatorial constructions, we could provide examples ad libitum, at liberty, because, but we're going to stop doing that, because to actually extract the coefficients involves lots of calculations with the techniques that we have. But when we get to complex analysis, we're going to be able to eliminate really a lot of those calculations and simplify them greatly. But that's a topic for second half of the course. So that's an introduction to parameters in labeled classes.